Welcome to my next video where I'm going to talk about more advanced test bench design. As a quick reminder, we are designing a 3-bit comparator that is using a 1-bit comparator as a building block. In short, this is the design. We started by building a 1-bit comparator that had inputs to determine if a previous larger bit is greater than or less than already, and if not, then we will quickly evaluate if the 1-bit X or 1-bit Y is greater than or less than. We strung 3 of those together in a design and put them inside a higher level design that is called a 3-bit comparator, so that we can hopefully successfully compare two 3-bit numbers. In Vivado, what you will see is that on the left side in the sources file, the top level design is now a comparator underscore 3-bit. If I expand the arrow, you will see that I have 3 1-bit comparators on the inside. This is as intended. This is called hierarchical design. In the simulation sources, I do not yet have a test bench for the 3-bit comparator. I do have a test bench for the 1-bit comparator that was discussed in a previous video. So what I need to do then is I need to design a test bench for a 3-bit comparator. I do this by hitting the plus button or the add sources button. I will select simulation source because test benches are never design sources. Hit next. I will push create file. I will give it a name, which I strongly suggest is the name of the thing that you are testing underscore test bench. TB for test bench. I will then hit finish. This will prompt me to create ports. In the case of test benches, we do not use ports. That's for the purpose of this class. There are, of course, exceptions to almost any rule that I tell you. You will now see that I have a 3-bit test bench down here, ready to be used. I will double click on it to open it. And the first thing that I need to do is I need to make the device that I would like to test available to this new design or new simulation file. I will do that by clicking on the design file I would like to test, selecting the entity, pushing Control-C to copy, going to the architecture header, which is where I make files, signals, and devices available to use, pushing Control-V, changing the word entity to component, and replacing the end statement with end component. I now have this device to use. You will recall from my previous test bench video that because we are not using any ports, I have no signals available to use, so I must create test bench signals. So I will do that by writing the word signal and creating names. I would like to you to remember that I append the underscore TB to be clear that this is a test bench signal and is not something that is inside of the device to use. So ATB, BTB, these are standard logic vectors of the same size of what I need to test. Similarly, I need signals that are LITB, GITB, and these are standard logics. I also have the output signals, Gout and Lout, which are also standard logics. Now, because these signals are the same type, standard logic, I could place them on the same line. However, oops, forgot the TBs. So the reason that I did not put them on the same line is because I like to give my input signals initial values. You will recall from the previous lecture that to do that for standard logics, I do apostrophes 0. Now, LITB and GITB will start at the value 0. For a vector, I need to do quotes and then put the number of zeros that I would like. In this case, 3. Alternatively, if it is a very large number, you may type the word others 0. This will fill in all other values, meaning all of them in this case, to 0. You don't need to do this. The quotes with 3 zeros is also acceptable and is less typing than others for small vectors, but it is useful to know for large vectors. Now that I have created all of the test bench signals, keeping in mind that I did not assign initial values for my outputs because my circuit is what's responsible for driving the outputs, not the test bench. Also recall that this colon equals for an initial value assignment will do nothing for generating physical hardware unless we create something called a constant, which we will learn about in this video. So, for the moment, I have made a component available, but I have not used it in my design. In order to use it in my design, I need not only the component declaration, highlighted here, I need a component instantiation. Just like in my previous test bench, I'm going to call this UUT because this is the device that I'm testing. I need to tell it what the name of the device is. And then I need to write the words port map, give a parentheses, and now I like to start by listing all of the ports that I need to use. So A is going to get mapped to something. Oops, sorry. There we go. I'm going to tab over so that they line up because I like to have good readable code. Specify that B will be mapped to something. LI, GI, Gout, and Lout. These are my ports. I must now tell it what signals are attached to those ports. Fortunately, this is very simple as it is just the port name with an underscore TB next to it. Very well. You will recall from my previous test bench that I initially did a process that has a begin, sets up the values, then wait so that you have time to look at the waveform, analyze what the outputs are, determine if they're correct, and then change the signal. So set up, wait, change, wait, change, wait, change, wait. However, this is horrifyingly tedious for large number of input combinations. In this case, we have a 3-bit A, a 3-bit B, a 1-bit LI, and a 1-bit GI for a total of 8 bits of input, which would be 2 to the 8 different combinations that I would, It's a lot of combinations that I need to do, and I don't want to write that much code. So we're going to introduce the for loop, constants, and assert statements. So what we would like to do is start with a process. We are always going to have a process in our test bench. And as I mentioned before in a previous video, anytime I write the word begin, I go ahead and write the end for that statement so that I don't forget. A for loop. Hopefully you know what for loops are. I'm not going to spend the time to go into depth on them, but a for loop has what's called a loop variable that it will increment through and go ahead and step through an automated sort of process. However, before I can utilize the for loop to the best of its ability, I need to create an array that has the values that I would like to store. Now, creating arrays in VHDL is a little bit odd. First, I need to create a new type by writing the word type. Then giving this type an array, which I'm going to basically call this input array type, which is a long word, but I never have to use it again except for one time. Then I have to tell it is array. Tell it how big is my array. Well, this is the inputs, which there are 3 bits. And I need to then say, well, 3 bits can represent 8 different combinations. So I'm going to say 0 to 7. Then I have to tell it what the data type of each of those indices are. So in this case, of standard logic vector 2 down to 0. Then the last thing that I need to do is put the semicolon. And now that I have this available array type, I need to create either a signal or a constant. Because these are the inputs and they don't change, I'm going to create a constant. Similar to a signal, but it never changes, which means that I can use the colon equals to create initial values that will stay. So constant, I need to give it a name. I'm going to create this as A's, meaning these are the list of all A's that I might use. I need to tell it what the type is. In this case, it is an input array type. And then I need to tell it what the values of that array are. I do colon equals, and I've already typed this out off screen because I don't want to type forever. But there I go. I'll give you the moment to look at this, but basically, this is one line of code that I have used returns on because returns don't execute in the way that's just for formatting, but I've made it nice and easy that I have all possible combinations of inputs. Now, I'm going to realize at this right now that I don't actually need to call this A's because my A and B vectors are exactly the same. So I'm just going to rename this to input vals to give it a input values basically is what it means. And in this way, it is more representative of what the array is doing. It's just a better name. Now, at this moment in time, I would like to point something out. There is a button that you can do to undo. That is Control Z. Control Z will undo whatever you last did. However, many other programs use Control Y as redo, that if you would like to undo your undo. But in Vivado, Control Y deletes the line. So here I put my cursor at line 51 and push Control Y, and that whole line disappears. If you're used to other programs where Control Y is the redo button, you may accidentally delete a number of lines and be very confused as to why your code doesn't work. So be very careful with the redo button because it is in fact Control-Shift-V. Very well. Now potentially I would need the LITB and GITB to iterate through as well. However, I am going to simplify this. The reason that these LI and GITB values exist initially, which I will show here, is if I have the LI and the GI, which I forgot to add, is because you could string two 3-bit comparators together, connect them up the same way these 1-bit comparators are, and you could end up with a 6-bit comparator. However, I'm going to stop at 3-bit comparator, so instead of mapping these to test bench signals, I don't want them to change, so I'm just going to specify that they are connected to ground or 0. They will never be active. This is a perfectly acceptable design choice. Okay, I have now created the port maps. I have connected up design signals, both inputs and outputs. I have created a constant array that we can step through, and I have the outline of a process. The next thing that I need to do is I need to apply those stimulus to the inputs. To do that, I'm going to create a for loop. A for loop has the following structure in VHDL. You say for the loop variable, I, in 0 to 7, loop. And then I write end loop so that I don't forget. Now, I will point something out at this point in time. I always strongly recommend using double characters for your loop variables, such as I instead of simply I. This is because both I and J for electrical engineers are imaginary numbers. They represent an imaginary number, and this is very easy to get confused with. So I, meaning doubling up the character for your loop variable, makes it very clear that it is a loop variable and results in much more readable code. Now, what we want to do with this loop variable is step through the various values of this constant input vals. And I want to put those values into the signal ATB, which is a standard logic vector. Great. So what I do is I say that ATB is going to get assigned to the input vals at the loop index. But since I want to test A's and B's separately for different combinations, I'm going to hit return, and I'm actually going to create an embedded for loop. So for JJ in 0 to... In fact, I'm going to introduce a new concept, which is VHDL has some object-oriented properties in that I can access properties of different signals, arrays, and similar. And I'm going to head and say that you can actually use something called range. Oh, I don't have the 0 to 7 set up right now. So I'll have to introduce that in a later video probably. So 0 to 7 instead. Sorry, got your hopes up. So for JJ in 0 to 7, loop, end loop. I would like to also let you know that you can actually name your loops. I don't do this very often, so if I screw this up, forgive me, but it's something like loop name colon, and then instead of end loop, you say end the loop name. It's just end loop. Okay, I guess it's just end loop. I always lose. Anyways, you can name your loops. I haven't been doing this. However, if you go out into industry, it may become the expectation that you name your loops. So keep that in mind as you move through your careers, that the way that I write code is not the only way to write VHDL. It is just my preference and my experience writing for industry. Okay, inside of this loop is where I'm going to assign BTB. But the nice thing is, it's going to be basically this same line, except for we're going to use JJ loop index. What this structure means is that for every A that I set up, I'm going to test all input combinations for B. Now this would run instantly, and I put that in quotes because it's not actually instantly. So we need to wait for some amount of time. I'm going to put that on the innermost loop, wait for 10 nanoseconds. And just like the other case where I don't want this process to run over and over and over again, I want to stop after I have tested all combinations, I will write the word wait right before the end process so that it runs through all of this one time, meaning all possible input combinations for A and B, and then waits, which is quite excellent. So now let's go ahead and run the simulation. But I will let you know that I'm going to run this incorrectly on the first try. So we would be tempted to hit run simulation. A waveform pops up. Just like before I mentioned, the first thing you want to do is push the zoom fit button right here with the 4 arrows pointing outwards. That will show you the full span of your simulation. And you might be initially thinking, oh, good, it's doing things. Well, the issue is, notice that none of these are vectors. So if you recall from our test bench, we had at least 2 things that were vectors. So what went wrong? The answer is I ran the wrong simulation. So let's go ahead and click this blue X up along this blue bar. There's the X here. This closes the simulation so that I can run a different one. And what went wrong is that over here in the sources menu, I have the comparator 1-bit test bench selected as my top level file as indicated by the green rectangle over 2 gray rectangles. That is the highest level of the hierarchy in my simulation files. This is why good names for your test bench is so important, is so that it is clear what I'm running. So I can click on that, right click, move down to set as top. Now when I run simulation, this is what will run. I would also like to point out that this is a description of the hierarchical design. So if I expand the test bench, there's a 3-bit comparator under that, and under there is 3 1-bit comparators. That also means, if you recall from the 1-bit or the 3-bit comparator, where I made a 1-bit comparator available, I did not make the 1-bit comparator available to the test bench. That's because when I made the 3-bit comparator component declaration, sorry, that's up here, that hierarchically allowed me to use the 1-bit comparator. So I don't need to list all of the components unless I'm using them directly at this level of the hierarchy. So just to recap, in the test bench, I have no ports. I create signals for the test bench and declare the component that I want to test. I have created a new type that is an array and filled that array with all possible values that I would like to test. I then created 2 for loops that will step through the indices of each of those values, 0, 0 up to 1, 1, 1. And we will be able to see what the result of my output is. So let's go ahead and click Run Simulation. I didn't think I ran. I don't know what this is telling me. This is not good, actually. I'm going to pause for a second while I figure out that error. Okay, sorry. I paused the video to figure out the error, and what it was is that I had a different window open that had another design file that I had from a previous example, also called comparator3b, and it did not like the fact that I was trying to run two simulations at the same time with the same name. So I have closed that other simulation, and now I've run it. Just like before, I'm going to click the Zoom Fit button. That allows me to see the full range, and you can see this runs for a much longer duration than my previous simulation. You can see that the inputs and outputs are changing, and in fact, you can see a couple of spots here on the waveform where they're neither less than or greater than are asserted true. This is excellent. Right, that should be where the values are equal. So we could go ahead and zoom in and say that, well, in the case of this point in time, oops, I'll zoom in here. At this particular point in time, A is 2, B is 5, there's no LI, there's no GI, which means that 5 is greater than 2. And the question we're asking is basically, is A less than B? It is. 2 is less than 5, so the less than output is true. Over here, where A is greater than B, the greater than output is true. So it looks like this circuit is functioning. The only way to be absolutely sure would be to view every single transition, which would be really frustrating, right? Because I have to go, well, 3 and 3 are equal, so neither output is true. I'm feeling pretty good about this design. However, it's not a perfect test, and so it would take a lot of time to fully analyze. The way that we can address this is if we go back here, I can create a new type. In fact, I'm going to basically steal a lot of this code because it's very similar. I'm going to create a new array. Instead of input array type, I'm going to call this the output array type. However, the output array has 6 bits, right? Or sorry, 6 bits worth of potential values. So we need to make sure that the size is correct. And it's not a standard logic vector, it's just standard logic because it's either true or false, right? These are the greater than or less thans. So the new size has a range of 0 to 64 minus 1, which is 63. Then I need to create the values, and this would be a list of all of the answers. So I know, and this would take a lot of work, if I'm honest. This is not my favorite way of doing it, but if I would say in the beginning, they're going to be equal. Then, because of the order of the loop, B is going to increment first. And since B increments, and we're asking is A less than B, that means that my less than output should be true. So I will have a 1. And then I would go through that, and rather than calling this input vals, this would be the less than vals. This is obviously a bit of an issue because I still have to write 64 different zeros and ones, and that's going to take me quite a while to design. A smarter way of recording then, or not recording, sorry, of testing this is actually to utilize the loop variables, because we know that as the loop variables go up, so do the input values. In fact, they're 1-to-1, basically. This is just, I've basically done a type conversion using a input vals. So let's do the smart, and instead, let's create 2 new signals. One of those is going to be the less than result. This is the expected result, and the other is going to be the greater than expected result. These are going to type Boolean. These are either true or false. That's the only values that these 2 can have, is they're either true or false. So let's come into here, recognize that I'm setting up ATB and BTB in this loop. I'm then going to slightly offset this because I don't like to set the values and evaluate the values at the exact same moment in time. So I split these out to make, and this is really just to make it a little bit easier to read. And now I'm going to say that the output, which is G out TB, right? Well, actually, let's use these LT results. Create the LT result first. So LT result is it's true if A is less than B. So ATB, oh wait, no, not ATB. We're going to use the loop variable for A, II less than JJ. If II is less than JJ, LT result will be true. Similarly, I will use the greater than result and assign it to II greater than JJ. Now I want to make sure that these are automatically tested. I don't want to have to look at each of these their own way, so I'm going to further split this out. Again, this is going to just be for readability of the test. This is not necessarily the best way to do it, but it's a good way to start. And I just want to keep it at 10 nanoseconds per iteration total is what I'm doing here. There's a statement called assert report. It's an assert report statement. Assert is saying that I am asserting that something is true. So if I assert LT result, so assert LT result, the LT result is the ideal, should equal the less than, right? So LT result should be the LT output, which is the L out TB. Put that equal, and if they're not, I would like to report bad comparison. Now this is going to be a bit of an issue, simply because the LT result, if you recall, is a Boolean, and the L out TB is a standard logic. We're going to leave that because there's no error. So if you typed this, you wouldn't know, and so we want to see what happens. So I'm saying that this expression should evaluate to true. That's what I'm asserting. I'm saying this is true at this point in time. If it's not, I'm going to write report bad comparison. That bad comparison will print down here in the TCL console and tell me at what time the problem happened. All right. However, I also want to compare the greater than result. So why not do both? Assert the GT result should be the G out TB, meaning if this is true, this should also be true, and I'm comparing true to true is hopefully what would happen. However, they're different data types, and VHDL never likes different data types to be compared. We have to be very careful because VHDL is what's called strongly typed. So we're going to go ahead at this point, and I have these new assert reports, and I'm going to run simulation. As expected, there's a simulation failed. So let's click OK. This pops up with an error message. These messages are completely worthless for helping you debug things. So you're going to just simply click OK. Then you're going to expand this window down here and click on the TCL console. Once again, the errors in red text are completely useless. However, just above those are errors in black text. Go to the first error in black text and follow it out and read what it says. This error says, found 0 definitions of operator equal, cannot determine the exact overloaded match for definition equal. If I scroll to the end, it will tell me that it is my comparator 3-bit test bench at line 82. This would be very helpful if I didn't already know where the error was, but it tells me what the error is, kind of. What this is really saying is that it cannot successfully compare a standard logic vector to a Boolean. It's confused. So let's minimize, go up, find line 82. It's right there. It's angry. This is a problem, as I expected it would be. So how do I convert a standard logic vector into, a standard logic into Boolean? Well, it turns out there's a really easy way, which is we're looking for LT result, which is going to be true if II is less than JJ. right, which is the loop variables, which is basically A less than B. So this is going to be true, and we want it to be true, so we just compare L to 1. This is now comparing the LT result calculated above to L out TB equals 1, meaning if L out TB is 1, being active, this will evaluate to true, this would be true, and we're good to go. This is a very crude way of doing this conversion, but it does work quite well. Generally. This may fail. I actually haven't run this simulation yet to make sure that this works. So now you'll notice that if I scroll up, there's still errors in this waveform, and we might get confused. We could see that I launched the simulation below that. The other thing I'd like to point out is over here on the right, anywhere there's yellow on this bar is a warning, and anywhere there's red is an error. So if I click on an error or a warning, it's going to jump right to that point. If you don't like the clutter of it, you can hit the trash can button. It will clear all outputs. I can then push this relaunch simulation button. And I can happily say that nowhere in here are any errors. There are warnings, but that's fine. I will then hit the zoom fit button. It has added the LT result and the GT result to the waveform for me, and everything is nice and happy. In fact, I have no bad sums available. I would like to show you what happens if there is a bad sum. So let's go purposely break something. So let's go into the comparator 3-bit. Here, if you recall, we wanted to connect the output GT to a signal shown in this figure. So this signal here is the GT signal that connects comp2's GT to comp1's GI. If I double click on GS1, you can show that is the output GT of comp2 connected to the input GI using the signal GS1. Let's suppose that I made a mistake and put GS0 there. GS0 is used later. This is going to be a very bad error. However, I'm going to hit this relaunch simulation button to establish that we are running a new simulation with that new design file. Be warned that when you click this relaunch button, Vivado, at least older version, have an occasional tendency to latch on a previous design file. So it is just good practice to occasionally push the X up on this blue bar, close the simulation, and run a brand new fresh one. This is the first time I hit relaunch, so I'm feeling pretty okay about it. And moreover, you'll notice that I have a whole bunch of errors. See, time, 479 nanoseconds. There's a bad comparison. I can scroll up until I find the first one. We always start by debugging the first error. And what it says is at time 19 nanoseconds, there's an error. In fact, the error that occurs is, well, what is it? It's not specified. There are advanced techniques that we can use that would actually report more about the error, but all we need to understand for now is let's go to time 19 nanoseconds. So, going to zoom in just a little bit. Remembering that when I push the magnifying button, the zoom, it zooms wherever I'm currently clicked. I'm going to find time 19 nanoseconds. And then I will point out this is why I split out this test bench into the wait for 8 nanoseconds, wait for 1, and then report, is so that it's easier for you to read, so that at time 19 nanoseconds is not the exact time that values are changing, which makes this very difficult to read. I don't want you to go through that, so just follow the kind of convention and you'll thank me. What you will see, however, is that at this point in time, Gout TB is undefined and Lout TB is undefined, and that's a problem. Right? We don't like that, but it's hard to tell why. Why are they undefined? Why am I not getting a value? Well, the way that we would debug this is we need to know what's going on inside of the other devices. To do this, you come over to the scope menu that is next to the sources tab. If you were in sources, you can click scope. The scope is what level of the hierarchy am I interested in signals? So if I click on the comparator 3B test bench file, it will show me signals, excuse me, that are at the test bench level. If I click on the unit under test, that will show me the highest levels of the hierarchy. If I expand this even further, I can go and look into individual bits of what's going on. And in fact, I can drag either individual signals over, or I can drag the entire component over onto this window and it will populate. Any signal that is directly connected to a test bench signal, meaning there's no logic in between, will automatically populate. Anything new, I'm going to have to rerun the simulation. However, I'm going to add all three of my internal comparators. And you can see that these outputs are what the test bench signal is directly connected to, and I'm already generating undefined, but I have not yet identified why. So let's hit the relaunch button. The zoom to fit button. Click where these errors start occurring, which in this case is the very beginning. And I'm going to recognize that the earliest bits, the first thing that calculates is this first set of signals that came from comp2. And by mousing over them, you can see that there is this comparator 3b underscore tb slash uut slash comp2. That's letting me know the scope of where I'm looking. So what I can see is that here, at this point in time, there is a GI that is undefined. That means that I have an input that is undefined, which is problematic. So, as an experienced designer, once you get there, you would go, oh, if an input is undefined, of course its output is undefined, right? This is both in the scope of comparator 1. The input is undefined, so the output is undefined. If you don't know what your inputs are, of course you don't know what the outputs are. So we would say, all right, this is in comp 1 that is the issue. Now, because comp 2 has no problems, I would use that to make the initial assumption that there's not a problem with my comparator design. Instead, there's a problem with the way that they're connected together. So I would go back to the area where I connect them together. I would go ahead and start looking for the signals, and I'd be like, well, it's GI. By double clicking on it, I scroll up and say, oh, this is connected to a port. That's good. This GI, double click on it, is GS0, but I see no double highlight between comparator 2 and comparator 1, which tells me very quickly that they're supposed to be connected and they aren't. So I change that to GS1. I double click. They're together. Now I've connected them. Now, hopefully, when we rerun this, the errors will all disappear. I see no errors up until that point where I ran the new simulation, that relaunch sim, and no errors, so it works. I would definitely, even if I wrote the assert report, I would definitely zoom into various spots just to check and make sure that it made sense of what was going on. You will definitely want to be able to read these waveform diagrams by looking at the inputs and determining what the outputs are, things like that, right? Just make sure that you are not having weird errors. So the main takeaway here, this type of a for loop with assert report statements, as long as they're intelligently designed, can save you a whole lot of time in designing test bench processes. Okay, so I will have future lectures. At this point in time, I'm not going to record them, so I don't want to commit to what they will be, but please plan on having a more detailed video in the future that talks about diagnosing errors. We will have videos that talk about synthesis, implementation, and how to push these onto physical hardware and test them there. Hopefully, though, for now, this gets you to the point that you can successfully design a wide variety of combinational logic devices. I would like to point out that if you were to design, say, a full adder and then build that into a 4-bit adder, for example, this process would be exactly the same as this video, meaning that step 1 would be to design a full adder. we designed a comparator here, you would instead replace this conceptually with a full adder. Then you would test it using a test bench similar to this one. The next step would be to create a design file called 4-bit adder, where you would create a component declaration for the full adder, and you would create 4 component instantiations, also known as port maps, for each of those 4 adders that connect together, where the carry out of one connects to the carry in of the next. Then you would design a test bench for that 4-bit adder, hopefully using a assert report statement, because that's the best way when you have something that has a bunch of outputs, which is the case with the full adder. You would then make sure that all of the results worked through the waveform and double checking with the assert report for all of them. Anyways, those videos conclude the design process for hierarchical design of combinational logic devices.